In terms of calculating the bond energy, we need to break this down into stages like we had done in the synthesis reaction. Now, the stages here are a little bit different because we are talking about a covalent molecule. There's no ionization energies and electron affinities because we're not forming ions overall. But what we can do is look at our overall reaction, and here we have the molecular models because that's going to help us visualize what's changing with the bonds. Now, if we notice in the propane molecule we're starting with, there are no carbons and oxygens bound together the way they are over here, which means that every single bond in that reactant must initially be broken so that when they recombine, the carbons can go with oxygens and the hydrogens can also go with oxygens. So the first thing that must happen before this reaction could run to completion is that every single one of these bonds in the propane molecule must be broken. They must dissociate. And to do that, it's going to require energy, because anytime we break a bond, energy is input into the system. So if we look up the bond energies of the carbon-carbon bonds in the molecular model up here, we see that the bond energy of carbon-carbon is positive 348, and there's 2 of those in that molecule. And in addition, there are 8 carbon-hydrogen bonds that need to be broken. So we can look up the bond energy of those 8 bonds as well. In total, we would need to gain 4,000 kilojoules of energy to break apart 1 mole of these reactants. So this sign's going to go up, 4,000 kilojoules. Now, once that's all broken apart, it still can't recombine with the oxygen because the oxygen is currently bound to other oxygens in the diatomic molecule. So before we can go to the next stage, we need to also break apart those 5 oxygens. Right? This double bond here, 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 and there, right? All up in these reactants. So each of those bonds has a bond energy of positive 495, giving us a total of another gain in energy of positive 2475 kilojoules. Now, in total, this is a really large activation energy, right? Around 6,500 kilojoules that need to be added just to initiate this reaction, which is why these combustion reactions need this spark or this little bit of heat to get themselves going. However, at this point, once everything is broken apart, we can start forming our products. And we know that when we form bonds, energy is going to be released as they become more stable. So the first thing we look at is the formation of carbon dioxide. We could do water first as well. It doesn't really matter, but I chose to do carbon dioxide. So in doing that, to form those 3 carbon dioxide molecules, we need a total of 6 carbon-oxygen double bonds. So looking at the bond energy of that one, it's 799. There are 6 of them. So now we're going to be releasing 4,794 kilojoules. Now to go form the water, there's 4 water molecules. Each of those has 2 OH bonds, so there's a total of 8. The bond energy for each of those is 463 kilojoules, and since we're forming them, that energy is going to be released. So we're going to be releasing a total of another 3,704 kilojoules. At that point, we'll have formed all of our products, giving us an overall energy change of negative 2,023 kilojoules. The total activation energy needed to get this reaction going and break all of those bonds is a positive 6,475. And so this diagram here gives us the overall energy change of this reaction. Now, in a combustion reaction, there's a lot of energy being released, as we talked about. It could be heat, it could be light, it could be kinetic energy. We often think of combustion reactions as the flames and fire. Fire itself isn't a product, right? The fire is the hot air, the hot gases being released. It's the light energy from those excited electrons releasing energy. It's also, particularly that yellow color, it's a black body radiation, which we talked about earlier in the year, about the light things can release when they're hot. And the yellow light itself in a wood fire is actually from heated up carbon atoms that aren't being completely burned. For example, when you burn wood or candle wax or paper, not all of the carbon is being completely turned into carbon dioxide, because there's not enough oxygen getting to it over the course of the reaction. If you are able to provide more oxygen to a flame, if you think about perhaps a really hot fire pit or something, or a forge, if you've ever seen blacksmithing, you actually don't see a lot of flame in those fires because there's so much oxygen getting to it that all of that carbon is actually getting burnt up. So there's no soot, no particles to give off that yellow color. Now, in this particular reaction for propane, notice that we're starting with one molecule of reactant, but we end up with 7 gas molecules at the end of the reaction. Right, so we're having a huge expansion here where we went from 1 molecule of gas to 7 molecules of gas. Now, if there's more particles of gas, that's going to take up a whole lot more space. So combustion reactions have a whole lot of different applications depending on what we do with the system that these combustion reactions are happening in. So think about some different scenarios we can make. Right? What happens if we do this combustion reaction inside of a container with a single opening so that we controlled which direction the gases could be released? What if we were able to do it in a container where there was walls on all sides, but one of them was able to flex and move a little bit? And what would happen if we did this in a container without any openings? Well, if we did it in a controlled container with just one opening, that's how we get rockets, jets, firearms, cannons, right? All of those things. All of those are examples of combustion reactions where the fuel is being combusted and then that hot gas is being vented or controlled in a specific direction. And as those gas molecules expand and are released from the reaction, they propel or they push other objects out. If we had this in a sealed container where a wall can move, that's how we get an engine, and what's called an internal combustion engine, like the kind that power gasoline-powered cars, lawnmowers, or any other kind of gasoline-powered motor. What happens is the air and the fuel mixture comes in. As it gets combusted, it pushes what's called the piston, right, that wall down, and spins the gears and turns the crank in the engine, causing the wheels to turn and the coal car to move. So making sure that the right amount of oxygen and fuel gets into that motor, into the combustion engine, to allow it to combust properly and efficiently is part of what leads to different levels of fuel economy in cars, and developing different fuels. And if you go get gas, you notice the different octane ratings, all those related to the oxygen content and the fuel content being put into the engine. And then lastly, everybody's always favorite, is that if we do this combustion reaction inside of a sealed container, eventually those buildup of gas molecules is going to be exerting so much force that the walls just can't contain it anymore. And that's how you get a bomb, right? A big kaboom. Now, as we talked about last time, we did talk about the different stages of these reactions, but it's important to remember that all of these 4 stages that we just did in this reaction example, for example, with the propane, they do occur almost simultaneously because as the electrons are being quote unquote lost from the carbon, they need to be gained by the oxygen, but it's not that they're ever in this transition state where they're not attached to anybody. Right, it's being pulled by the oxygen, so they're actively going from one to the other through those changes in attractive forces. So for the assignment for this, we're going to be making another summary infographic or slide or drawing, however you want to do it. This is what I put together for my example that I did across the last couple slides with propane. So you can look to do something similar to this or what you did for the last assignment as well.